Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 3.2 in the Big Ideas Math Integrated Math 1 textbook on linear functions. Now this chapter is called Graphing Linear Functions. So it sounds like in order to graph them, we want to know what they are. So this section seems pretty important. I don't have much to say about it before leading into it. I have a lot to say about it when we do. But we have, I think, 54 questions in total, so a bit more than before. We might have to do some graph things as well. Jump to the description section down below to find this PDF of the actual section, as well as graph paper if there's something you'd like to print out, if provided, if needed. Otherwise, we're going to start doing the graphing pretty soon here on out afterward. And then problem sets and timestamps down below as well. Without further ado, let's go ahead and get started. We're going to identify linear functions using graphs, tables, and equations. So figure out when they're linear when you have any of those three representations. Oh, we will be graphing them using discrete and continuous data. Data probably means sets of points of some sort. I said these words, by the way, in the last section quite often, and now they're going to be referring to them here, at least discrete and continuous. They probably kind of should have done it in the last section, but that's okay. We'll restate them again. And write real-life problems to fit data. We'll see what the heck that means within. Now, there are a lot of different phrases here that, it's one of those things where I don't know how much reading this will help us as a whole, other than kind of summarize the points when we hit them. But I'll kind of dance around those things. Everything says the word linear, which is linear except for non-linear, of course, because when we have to identify something that's linear, we have to say what makes it linear versus what makes it non-linear, or something else non-linear. So yeah, let's just kind of look through this thing, identifying linear functions. So an equation that can be written in this form will be a linear function, y equals mx plus b. Now this is one that I've teased quite often. If you remember section 1.5, we were solving literal equations. And remember what I said? I like to put my x in front. I like to put my x in front. This is why. This is a graphical representation that we're actually going to be quite used to. And we're going to start graphing, I think, later in this chapter. Now the fact that it can be written in this form means there's a y variable, there's an x variable that could be present so long as the m and b are certain values that would keep them present. They're both raised to the first power. They're not multiplied together, and they're not in denominators of a fraction. Now it says m and b are constants. M and b could both be 0. M and b could both be fractions. They could be negatives. They could be, for some reason, raised to powers. They could be irrational. But x and y, as I stated, separate terms, present to the first power, not being divided in their own set, things like that, and not multiplied together. So separate. The graph of a linear function is a line. You see the word line in linear. You also see the word ear in linear. And if you listen, that has nothing to do with it. We see the word line. A linear function is a line. That's what you'll see on that. So equation base, we can present it in this form. Do we have to write it in that form each time? No. Is it a great graphical form when we do it? Absolutely. But as long as we can do those things that I mentioned, check off that list, that's good. Graph makes a line and a straight line, a non-redirecting line. A linear function also has to be non-vertical. So remember what I stated, that the x term is only present if m is not 0. Well, if m is 0, 0 times x means it's just 0 plus b, which means that goes away. A y equals equation like this, actually, and you might not know about it yet right now, that happens to represent a horizontal line. But y needs to be present in these equations, because if that goes away for some reason, well, now you actually have a vertical line. I know you don't probably know that yet, but that would be a vertical line, and that's a no-go. So linear functions can be any kind of line, but it can't actually be vertical, because that is not a function. That is not a function, right? So keep that in mind when it comes to these. A linear function has a constant rate of change and can be represented by a linear equation in two variables. So constant rate of change just means each time x increases by 1, y increases by equal amounts. And that's going to be present when you see those in equations more. We'll see them in tables as well. A nonlinear function does not have a constant rate of change, so the graph is not a line. So as we'll see in a table, as x increases by constant amounts, if y doesn't increase or decrease by constant amounts, nonlinear. Just maybe not a certain kind that we're talking about, maybe not a quadratic, maybe not a cubic, maybe not a rational radical, whatever, but it's for sure nonlinear. So let's take a look at some of the examples here. Let's look at the graphs. Is this a linear function? Is that a linear function? B is a line, so B is a linear function. This is not a line, so it's not a linear function. Literally, they say explain. That's the explanation there. Is a line is not a line, right? Or is a line is not a line. I mean, that's it, which is really nice for this. This means a lot of different things. Also, that means that it's not a constant rate of change of y. It also means that it can't be written in this form, all that. But as a graph, that's a representation. When we look at tables, we look for constant rate of change, part A. As x increases by a constant amount, you can either add 1 each time, or in this case, add 3 each time. We're looking to see if there's a good pattern for y. Y happens to decrease by 6 each time x increases by 3. That means there's a constant rate of change as y changes by a constant amount, or as x, so does y. That means that would be indicative of a linear function. Now, we only see it for a few points. We don't see it for its whole picture. We're going to have to assume that the rest stays in that pattern. That's all. This one, however, as x increases by 2 each time, y seems to change by different amounts. Now, you might say plus 7, plus 11, plus 15. Those are adding 4 each time, which means this is plus 19 next and plus 23. And I'd agree, that would probably happen. But that's actually not indicative of a linear function. That's more indicative of one of these kinds of functions, a quadratic function. So not linear, or not a constant rate of change. Therefore, it's non-linear. All right, so some monitoring progress. We can say straight up, linear and non-linear. No, they make lines. They need to make one line. This is called an absolute value function, actually, which has some constant rate of change, but not everywhere. And it redirects, not a line. All right, identifying linear functions using equations. Let's take a look at some of the equations and say, can we rewrite it in that form? All that kind of stuff. It actually seems like, based on this example, they might want us to do so, or at least indicate that if you can do it in that form, it's linear. We look at y equals 3.8, y equals square root of x, y equals 3 times the x root, y equals 2 over x, y equals 6 times x minus 1, x squared minus y equals 0. 6 different examples. They're saying which of the following are linear functions. They're saying you can't rewrite these 4 in the form y equals mx plus b, and they're right. Y equals the square root of x. Square root, a radical function, also means, even though you don't know this, it's raised to the 1/2 power. That's not the same as being raised to the first power. This one, so as long as it's buried inside of a radical, you're going to say it's not going to work. 3 to the x power, the x is in the exponent. It needs to be a grounded x value, so that's not the case. That's an exponential function, also not linear. This x is in the denominator of its own equation. Now, before you say, we can multiply both sides by x like this, you'll now notice that x and y are multiplying together right here to make 2. X and y need to stay separate. So this too is not a linear function. This one actually works. 6 times x minus 1. You can distribute the 6 into both of these. They do the same. You get y equals 6x minus 6, a linear function. This is y equals mx plus b form, right? This actually literally is written like that. And x squared minus y equals 0. This x is squared, not to the first power. Once again, one of those things that even if you subtract it over, it's not in that proper form. This is actually one of those quadratic equations. Now, the one that I skipped was y equals 3.8. Let's go back to that one again. That can be rewritten as y equals 0x plus 3.8. As I'll remind you again, the x can disappear. That doesn't mean that it can't be present if you do something specific with it. In this case, multiply it by 0, right? If the x term isn't there, must mean that that m value is 0. And because it can be written in that form, that means it is a linear function. And it's a specific kind. That would actually generate a horizontal line given that 0 or given that the x is missing, which is, again, when we graph them later, we'll play with those when we need to. So there's a concept summary here. Let's see what I want to refer to. Representations of functions. Just to remind you of what functions are. In a table, x's can't repeat with different y values. In an equation, you can only substitute one value of x. For every value of x, you can only get one y value out from it. And I don't think we're going to be looking at any equations. Even the equations you saw up here, guys, if you plug in a certain value of x, you are only going to get one value of y. So those are actually all functions. They're just not all linear. In the mapping diagram, any element in the domain cannot map to multiple elements in the range like that. Otherwise, it's not a function. And this needs to pass the vertical line test. And this one does. So these are all functions in that way. I don't know if all of them are linear, but they're all functions. They look linear. Graphing linear functions. We're going to get a little bit of that as well. A solution of a linear equation in 2 variables is an ordered pair that makes the equation true. I want to repeat. We've probably checked for solutions more often than not. Every time we solve for a variable, we plug it into the original equation to see if the left side equals the right side. That makes what we had a solution. Now our equations have 2 variables. We'll have to substitute both of them inside of there to make sure that the left side equals the right side, if that's what they actually ask for us to do. What we are going to do, however, is draw a graph to represent all of the solutions of the scenario. And I think most people don't understand why we actually draw graphs, besides like word problem things. Graphs represent solutions and all the points. You know, when you draw a graph, when you have an equation with x and y in it, there's not just one answer. It's not just, oh, x equals 1, y equals 3, that's it. No, when x equals 2, y is 7. When x equals 3, y is 11. Right? When x equals -2, y is this. So there are different answers, and there's an infinite number of answers. And all of those answers are represented as the graph. All the points that we plot and we connect just to show that all the ones in between interpolate all those solutions as well. Every single thing on there makes a solution. And that's what they're saying. A solution is an ordered pair that makes the equation true. The graph is the set of points that represents all the solutions. So when we say in a graph, this is a solution, this is a solution, this is a solution, and these are all solutions, and in between are all solutions as well, that graph represents all the x, y values that would make the left side equal the right side in such an equation. So I probably stated a lot more than they did, but I want to make sure to interpret what that is, and so when we actually do the problems, we can work it out. Now I'm going to go pretty shortly on these because I mentioned these quite a bit in the previous set. Discrete relations are ones where you have a separation in your values. They're finite. You can actually write them out. 1, 2, 3, 4, 5. Whereas continuous is an infinite set in between two values. It hits every point in between. Continuous. For me, the way I define continuous to most people is I say, if you can draw it without lifting your pencil off the paper. To go from here to here, I can't lift my pencil off the paper. That means all the points that it hits is continuous. Discrete, I have to lift my pencil off the paper. Boom, 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 boom. So discrete, separation, continuous. Continuous, like that. So with respect to domains and such, they'll probably talk about this is written as a list, this is written as a compound inequality or some sort of inequality, or all real numbers. Depends on the question. Here's an example of graphing discrete data. Discrete. The linear function y equals 15.95x represents the cost y in dollars of x tickets for a museum. That means every time you increase your ticket amount by 1, you're spending another $15.95. Or they're earning that much or whatever. That's the functionality of it. Find the domain of the function. Oh, each customer can buy a maximum of 4 tickets. So find the domain. The domain represents all the different x values that can possibly exist here. So we think about this. You can either buy a ticket or not. That means you can only have 1 or 2. You can't have 1.5 tickets, right? You can't have negative tickets, and you clearly can't have more than 4. A maximum of 4 tickets, so you can't have 6 or anything like that. So what's our list of possible tickets you could buy? You might think 1, 2, 3, 4, and you're close. You could also not buy any. So you can buy 0 tickets, 0, 1, 2, 3, or 4. So let's look at that scenario for domain. Domain is 0, 1, 2, 3, and 4. Now, it's discrete because, again, not because they're whole numbers, but because they're separated values. It's not you can buy also a quarter of a ticket and things like that, and it kind of flows from 0 to 4 or anything like that. So it is discrete as a result of being a separation of values. We write our domain as a list. Now they said graph the function. In order for us to graph the function, we use this equation. This equation, we have this x multiplied by 15.95. We know the different values of x we can use in our domain. 0, 1, 2, 3, and 4. When we substitute them out, we get y values. We did this for at least one problem, probably only 1 or 2 problems in the last section, but we didn't graph them, and we also didn't write them as ordered pairs. When x is 0, y is 0, 0, 0 is a point. That's also on your graph, and that's right here. Now, I'm not going to spend time talking about how we do graphs or anything like that, but one thing we have to be careful of is our scaling. So 15.95, very close to 16. You might as well make it a 16. But anyway, 1 ticket is $15.95. 2 tickets is $31.90. 3 tickets, etc., and 4. And then we plot those points. They appear linear as well. I don't know if they're going to talk about that. They appear linear in nature, even though we don't draw a line through them. If you drew a line through them, you could literally draw a line. Why don't we draw a line through them? Because it's a discrete relation, not continuous, right? You can't buy half a ticket. So that's the idea there. Plot the ordered pairs, domain's discrete, so it consists of individual points, not a line. Anyway, these are all solutions to the equation, which means if I substitute 2 for x and 31.9 for y, I would make the left side equal the right side in that scenario. Okay, some more on the lecture portion, graphing continuous data. Here we go, another example. How do we determine it's continuous, right? A cereal bar contains 130 calories, and the number C of calories consumed is a function of the number B of bars eaten. says, does this situation represent a linear function? Well, it seems it does, because every time you eat another bar, a constant increase, the number of calories increases by another 130. They say the same thing. B increases by 1, C increases by 130. That's a constant change. Let me clear my throat 1 second here. Sorry, I didn't want a graveling voice sound to appear there, and it might happen again. I've been talking a lot. Yep. Find the domain of the function. Is it discrete or continuous? Now, the thing about this one, and I want to see what they explain. Yeah, okay, I was going to say the same thing. Was for the bar, for a ticket, you either buy the ticket or you don't. For a bar, I ate half a protein bar this morning, and I put the rest in the fridge. I kind of just want it later. So I ate half a protein bar. I didn't eat the whole thing. Little chomp, right? Little fraction of the bit. You don't have to eat the entire bar. No one's forcing it on you. It might spoil. Stick it in the fridge. But no, yeah, you can eat a fraction of a bar. You can eat part of it. So it can be any value greater than or equal to 0. Can't have a negative bar. It doesn't seem to max out anywhere either. So it says the domain's greater than or equal to 0. It's not a compound inequality. There's no limit to how many bars you can eat. Your calorie intake just goes up. So it's continuous. But they still plot specific values for B. 0, 1, 2, 3, 4, etc. Now, why don't they plot fractional values? Because fractional values suck to calculate. Why would I plot 0.67023 as a value to get that Y value out when I could connect those dots showing that relationship after? Now, I have to stress here that any 2 points do make a line. So even if I only plotted 1, 130 and 4, 520, I could have made the same line. But this is for precision's sake, and you're going to see this whenever we learn how to graph points, plot points really quickly. I'll always say in my window range, plot as many points as you can fit. Get it as precise as possible for as long as you possibly can. Even if you can draw a line through any 2 points, you can also draw it through 5 collinear points, which is part of the point. So we do the relationship. They say make an input-output table. For the sake of this section, we're probably going to have to do the same thing. Now, how far do we actually go? They went up to 4. I guess 5 points is enough. 0 to 4. We'll make a determination based on each problem, and I'll do what I can. Anyway, the equation. What's the equation here? Where is it? They never gave us one. Well, this one's more of the pattern. Every time the number of bars increased by 1, every time you ate another bar, you consumed another 130 calories. So this one's more of just adding 130 each time. Can you make an equation out of it? Totally. And a linear equation represented in that y equals mx plus b form. Until they ask us to write that for ourselves, we're not going to do that just yet, I assume, unless there's a critical thinking question in the matter. But every time we add 1 to what I would call x, your domain values, your input, your output's increasing by 130. They do say draw a line through the points because it is continuous. They also mention an arrow. Use an arrow to indicate the line continues without end as shown. Now, it's continuous. Now, here's the problem. They mention the word continues here to say this graph goes on forever. That's not what continuous means. Continuous means that there's an infinite set of points between any 2 points that we have on the graph. That doesn't necessarily mean it goes on infinitely. This one does. It doesn't go on infinitely in this direction, right? It just starts at the origin. To go on forever means it's continual, not continuous. Get the picture? But because of the infinite domain, there will be an infinite range. I can eat 1,000 bars, therefore I'll have 130,000 calories and also be dead. Maybe over the course of a lifetime, we'll see how that works. But it's a line with a domain here. Okay. And not done with the lecture portion. Okay, here we go. Writing real-life problems. Real-life problems write me, you know what I'm saying? Write a real-life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? Explain. So, I don't know. I don't want to read what they put just yet. I want to make up my own here. When x is 0, y is 6. When x is 1, y is 5. You could say, so as x increases, y decreases. It's discrete, and it's by a certain amount each time. There are 6 apples in the basket. Every time I take 1 apple, then there is 1 less apple in the basket, right? I have an apple, now there are 5. I take 2 apples, now the basket is 4. That's a pretty simple one, right? So let's take a look at what they say. You want to think of a real-life situation. Okay, so you want to think of a situation in which this happens. One possibility is 2 people bidding against each other on 6 coins at an auction. Each coin will be purchased by one of the 2 people because it's not possible to purchase part of a coin. The domain's discrete. Yeah, and listen, I'm not going to cut part of an apple at a store. I'm either going to buy the whole apple or not, right? Even though I can eat half an apple or not. But for this auction thing, either you take the coin or you don't. And if you do, then the person doesn't have it. The opponent, the rival. In this continuous relation right here, Maybe it's an apple juice thing. I have apple juice in this jug, and for every 6 gallon jug, no, 6 ounce apple juice cup. I drink an ounce of apple juice, then there are 5 ounces of apple juice in the cup, right? Or I drink half an ounce of apple juice. This is now fluid. There's continuous stuff here. There are fractional amounts. I drink the entire thing. This is empty. So that can be the same kind of thing. Continuous ounces of gold dust at an auction. So same thing, fractional amounts down to the micro little bits of it. So all the dust will be purchased by the two people. You can purchase any portion of the dust that makes it continuous. Very interesting versions that they had there. Okay, now we get to at least the vocabulary and core concept check. So that's a lot to state, and we do have 54 problems as a whole. So this may be one of those longer videos, especially if we have to explain why something's linear or not. We do have 4 questions to begin with here, and let's get them started. Number 1, complete the sentence. A linear equation in 2 variables is an equation that can be written in the form y equals mx plus b. This will not be the last time you have seen this, where m and b are constants. Get used to saying that one out loud and writing it and knowing it as well. Vocabulary. Compare linear functions and nonlinear functions. Well, it depends on what you're talking about. Graphically, it's where you have a line, right? Graphically, or graphically. Graphically, line versus not a line. Equation, written, can be written in y equals mx plus b form versus not. Obviously, these are the Cliff Notes versions of them. Table, constant rate of change versus not. And table would also equate to ordered pairs in a list of ordered pairs if you had them written that way. Those are the 3 that I'm going to use there. Compare discrete domains and continuous domains. And I've talked about discrete relations and continuous relations. This means the same thing here. I have my layman's terms version of continuous if you can draw it without lifting your pencil from the paper kind of thing. And discrete, you'd have to lift your pencil. You can say that. Discrete, I just say separation of values and that of specific values. And then whereas continuous, there's that flow of the values. They're all joined together. Continuous values are joined together at the hip. I don't know. That's still layman's terms version of it, meaning a basic term that you can understand, and I hope we still feel that out as we go. In situations, there's more that we have to talk about, right? Can you have a fractional amount of something and break it down to its smallest atom? Writing, how can you tell whether a graph shows a discrete domain or a continuous domain? Okay, so now they're talking about the graph. So now I can use my version that I stated. But discrete points, again, are separate. Points are separate. You can lift pencil from paper. Whereas continuous points are connected. All points are connected. And that's kind of what I stated for number 3. So now I have trouble kind of coming up with what I'm going to say. Oh, discrete and continuous domains. I'm sorry. They did say domains. Okay, when I write domains here, I write them as a list. Written as a list of numbers. Let's say that. And then continuous, we'd say written as an inequality. Perhaps compound. Perhaps it can be all real numbers. It can be all real numbers in that case. In a continuous state here, points are connected, meaning you don't lift the pencil from the paper. So there we go. I didn't know that this next question was coming up, and hopefully that makes sense how I change them up. Trying to put a colon there. And bold that statement, man. Let's make sure that we know. You already know what it is. Okay, guys, that's questions 1 through 4. We're now going to get to the official problem set 5 through 54. It does seem that we're going to have to do some graph stuff. So again, if you want to download the graph paper below, you can go and do that. We'll see how we're going to go about choosing our values for our table and what kind of situations they are. Without further ado, I'm going to go ahead and get started. On numbers 5 through 10, determine whether the graph represents a linear function or not. Explain. Now, pardon me as I do not copy the problems over. I'm going to leave them as they are. So for numbers 5 through 10, I'm just going to answer the basic question here. Does it form a line? So here's what I'm going to do. I'm going to create a template above for myself. I'm actually going to even do this. Let's see. I'm going to create this for myself, and I'll say if it's linear because the graph is a line versus nonlinear because the graph is not a line. something I'm going to pull from each and every time that we have a problem. It's going to make it very easy for me and you can follow along. Or maybe you already know the answers, you finish them and you're good to go. I have 6 problems here. Number 5. That is nonlinear. The graph is not a line. Look at that. I can just pull right from there. In fact, let me do this. 6, 7, 8, 9, 10. Watch me do 5 problems in record time. Number 6. Is that graph a line? Yes. Is it linear? Yes. Number 7. Is this linear? You betcha. How come? The graph is a line. Number 8. Is it linear? Uh-huh. The graph is a line. Now, I'll talk about, okay, they don't have it in the set. Number 9. I have 2 lines, sort of. That makes it non-linear, though. If it's a V shape like that, not a line in that case. And number 10, also a curve. Can't draw a line through that one. It's also nonlinear. Now, what they didn't show was a vertical line. That wouldn't be a function. It would be a line, but it's not a linear function. So they didn't show it. They didn't show it. But if they showed you a vertical line, that would be a nuh-uh kind of scenario. Let me now get rid of these things here. Bye-bye and bye-bye. Thank you for coming in. I hope we have more questions like those in the future. No, that's okay. We have to learn some more things. Numbers 11 through 14 determine whether it represents a linear function or not. Explain. These ones I'm going to actually copy and paste over just because I have things to actually do with them. And what I have to do with them is determine what kind of rate of change y has as x has a constant rate of change. And you have to be careful. You make sure that x exhibits a constant rate of change. You know, I'm actually doing some stuff in IM3 when it comes to is something a constant rate of change or not. Not to be linear, but to be some different kinds of polynomials and exponentials and things like that. I guess I missed that part right here. Anyway, x is increasing by 1 each time here. So as this is a constant rate of change, we have to see what y is doing. So we agree, x is all good. Y is adding 5 each time as x increases by 1. That is completely indicative of a linear function. So I probably could have a new copy-paste kind of format here. So I'll just say it's linear. As x increases by 1, y increases by 5. Constantly. They're both constant, but we just want to just kind of state how that works out. Number 12. Sorry. I have 2 different little screens to go from and to each time, and I have to change all my little tool things. This takes more work than you know. Hope you appreciate it. All right, x's are increasing by 2. Is that allowed? Of course, x can increase by whatever it wants. It can say 2, 3, and 4 as far as we care. It'll be hard to tell what y is increasing by this time, but because it's constant, we just have to ask. We have to ask if y is constant. -9 plus 6 is -3. -3 plus 2 is -1. The moment you see that, there's breakage. It needs to increase by a constant amount each time. Doesn't matter if the next 20 of them are plus 6 or plus 2. As long as there's a difference in any 2 while x increases by a constant amount, it's no good. That being said, it's never the same each time here. I don't know what it's doing as a whole or what kind of function this is. It's a function. It's a function so far, but it's nonlinear. As x increases by 2, y does not increase by a constant amount. By the way, y can also decrease, as can x, and I doubt they'll show x's decrease in these cases, but they're allowed to decrease. They just need to change by a constant. In fact, they don't have to change at all. Changing by 0 is a constant change of nothing as well. And so those can happen. We can have decreases, which is accepted. Case in point, we look at this one right here. So long as it's constant, we'll be good. So number 13, we can see x is increasing by amounts of 4. But like I said, x is likely to increase in these ways. When we go left to right, it's unlikely they'll show a decrease. They could, and if it's constant, that's fine. In this case here, we subtract 4, and then 5, and then 6. And I can tell what the pattern is. Having a pattern doesn't make it a linear function, right? This is nonlinear as well. Same reason as above. As x increases by 4 constantly, y does not increase by a constant, or y does not decrease by a constant amount. Now, you could make those kind of silly arguments. Y can increase by a negative number, therefore it's a decrease. So if you just want to use one word increase each time, I'm cool with it. Just make sure that if you state Like if something does decrease like by 2 each time, you have to stay, if you say the word increase, then I guess you got to say -2. And I wouldn't say decrease by -2, right? That's actually a double negative. So yeah, it is you do have to be careful on your words and your signs on these things. Now number 14, x is increasing constantly by 1. So there's a good check. Now let's check on y. Let's make sure our math holds up. 35 minus 15 is 20. Minus 15 is 5. So far, so good as far as linearity goes. Is 5 minus 15 -10? Yeah. And to even things out, I think we need 2 of them that are linear, 2 of them that are non-linear, things like that. So this is linear. As x increases by 1 constantly, y decreases constantly by 15. Okay. Okay, now let's go to exercises 15 and 16 where we do some error analysis. To correct the error in whether the table or graph represents a linear function. You see in this table, they're adding 2 each time, x increases there, and y is doing something. You might say, oh, plus 12, plus, I don't even know that number, plus 48, plus something, right? Oh, that's not linear, and you'd be right, it's not linear. It's not increasing by a constant amount. But they found something. They found out y multiplies by 4 each time. I don't know if you noticed that. Times 4 times 4 times 4. And that's true. There is a pattern to this, and it's that. Does that make it linear? No. It doesn't increase by a constant amount. It grows by a constant ratio. That's not the same thing as a constant or a factor or whatever. That's not the same thing as a constant multiple. So that one's different here. That would be actually indicative of an exponential function. This function is not linear despite the constant pattern that they found. If it is not a constant increase / decrease by addition or subtraction, then it is not linear. Period. This is actually, again, an exponential function. Not that you have to know what that is, what that does, so to speak, but it's not. And anyway, so that's our conclusion. It is not linear. And again, what we're doing here, I'm going to say it this way: plus 12 and then plus 48. Right there shows that this breaks as far as addition goes, despite the fact it's times 4. Let me pause for a moment here. Okay. Okay, number 16. Okay, perfect. Okay, this is where they have it. The graph is a line, so the graph represents a linear function. Here's the thing. It is a line. It's a linear equation. It's not a linear function. A function needs to pass the vertical line test. This one does not. A vertical line fails its own vertical line test. And if you remember what a vertical line test is it's a way to show that through a vertical line, you're never passing through more than one point. Here, you're passing through an infinite set of points when x is -3. So, although this is a linear equation, it is not a linear function. Only non-vertical lines can represent linear functions. Vertical lines fail vertical line tests. That's just my thing. Okay, anyway, so the graph's not a function because it's a non-linear function because it's not a function, despite the fact that it's linear. Okay, numbers 17 to 24, determine whether the equation represents a linear or non-linear function. Explain. Now, I'll have you know that these are probably all functions. I don't know for sure. They're probably all functions. You're hard-pressed to find ones that actually are not. There is a specific thing, and I don't see it. But are they linear or not? We're trying to look for, can we write it in the, y equals mx plus b form. So number 17, y equals x squared plus 13. It can't be written in that form, y equals mx plus b. Now, that's going to be the reason why it's not. I'm not going to write that each time. I'm not even going to copy and paste that each time. But if it can't be written in y equals mx plus b form, the m in this case, if it could, would be a 1. That's fine. But this is y equals mx squared plus b. The mx plus b literally means, actually just write that here, it literally means that y is to the first power and the x is to the first power, among other things. If you were with me on the lecture portion of this, then maybe you heard some things that I said about them. And I'll try and keep all this criteria in play. In this case, not a function. I'll put yes or no. Excuse me, not linear, non-linear. Non-linear because the x is squared. The x is squared. I'll write that instead of not written mx plus b form. Oh my goodness. That is just terrible writing. All right, number 18. You can see why sometimes I don't want to write more things than not. Y equals 7 minus 3x. Can this be written in y equals mx plus b form? And that's kind of a weird way to state that, oh, this is the reason why it can, whatever. But it works that way, and it's something that we're going to rewrite in quite a bit. Can this be written in that form? Swap the x term and the constant term here. This is a negative 3x, and that's a positive 7. Yes, that can be written in y equals mx plus b form. Look at that. Y equals mx plus b. M can be negative 3. B can be 7. Number 19. Y equals the cube root of 8 minus x. Okay. So, first of all, let's rearrange them into that other order. X is negative. Cube root of 8 is positive, like so. And ask yourself, is this good? Where's my m? Where's m? I see a negative sign. I don't see an m. That would mean m is negative 1. Negative 1 multiplying by x there. And it says plus b. Mr. Robinson, there's a cube root there. You can't have that in mx plus b form. M and b just need to be constants. B can be 0. B can be an irrational value. B can be a billion. It doesn't matter what b is. B can be whatever it wants. In fact, you guys know what the cube root of 8 is? You might not, but it's 2. 2 times 2 times 2 is 8. 2 cubed is 8, therefore cube root of 8 is 2. The mx plus b version of this that I can write here is negative 1x plus 2. And it doesn't matter. Listen, this could be cube root of 6, which is an irrational value, and it can stay that way. It's still linear. This is, yes, linear. It can be written in that form. So, yeah, it's the x that can't be in a cube root. It's the y that can't be in a cube root. But b and m, yeah, they can totally be in that. Number 20, y equals 4x times 8 minus x in a quantity. This one would require some distribution, perhaps to levels that you might not fully know on how they work, but you can distribute. This would be y equals 32 times x minus, now 4 would multiply by an invisible 1, so 4. And x times x is x squared. Y equals mx plus b. B can't have an x term in it right there. You have an x squared term. This is another quadratic equation. This is non-linear when simplified. So a lot of this looks like, yeah, we need to rework these equations a little bit. And I'm comfortable with that. Now, number 21, listen, you don't need to do that, but if you do, you can give that reasoning for if you can put it in that form, you're all good. This one, for example, I want to state out loud, guys, this is a linear function on number 21. The y and x are separated. They're both raised to the first power. They're not in their own exponents or denominators of themselves. There's only one instance of them. So that means eventually I can rewrite this in y equals mx plus b form. So it is a linear function, but let's enhance that a little bit more by showing y equals mx plus b form. I'm going to subtract 2 from both sides. And then I'm going to multiply both sides by 6. 1 6 times y means if I multiply by 6, that goes away. And 6 needs to distribute into both terms, like so. 6 over 6 is 1. We have y equals 18x plus 12. That's y equals mx plus b form. So yes, I don't really need to box that, but yes, we wrote it in the form, therefore it is linear. Number 22 is more of the same. This would also be linear. Now, on number 22, we have separate y terms. We have separate x terms. That doesn't mean we can't combine them if we move them to their own sides of the equation. The y's and x's themselves are separated, raised to the first power, not in their own exponents, not in their own denominators. If we do enough work here, we can make it happen. Now, the first thing I want to do here to make it happen best is I want to multiply everything by 3. Get rid of the fraction. I don't want the fraction. If I multiply everything by 3, then the 3 at least divides by this 3 to become 1, and it distributes the rest of them. Will we have to deal with something on a fraction perhaps later? Sure. 3y minus 3x equals 6x minus 2y. 3 divided by 3 is 1 times negative 2 is negative 2y. Now we can get y's on one side of the equation and x's on the other side of the equation. Let's rewrite it in that form, because I still want to show you something else with this. Add 3x to both sides. I might have to sneeze here in a moment. Let's hope I don't have to. Oh. No, I don't want that on recordings. Okay. Maybe you got to solve the rest of this for me. Is this y equals mx plus b form? No, because y is not by itself. Let's divide by 5. And now we get y equals 9/5 x. And don't you dare, outside of reduction of fraction, don't you dare write this as a decimal for this form, unless it's a word problem as well. And don't you dare write it as a mixed number. This will be your favorite number, your favorite version of the number that you have in improper fraction. Trust me, this when it comes to graphing. Is this in y equals mx plus b form? Y equals mx plus b. Where's b? B is 0. Is that allowed? Yeah. Yeah, it is. This is good as well. Yes, this is a linear function. Let me take care of sniffles now that I sneezed. All right, I did what I could in 4 seconds time. Okay, number 23. Do I ugly sneeze? Did I sneeze off camera? I have no idea. 18x minus 2y equals 26. Oh, this is so standard form. Excuse me, this is such a linear function, which is so standard form, which is a linear function. Yeah, this is totally good. Again, you can rewrite it in the form. You should be able to look at these. This is actually another criteria that some people will often say, books, websites, things like that. They say, if you can write it in ax plus by equals c form, you also have a linear equation, and this is that. Now, slope-intercept form is also something else we're going to get into, which looks like y equals mx plus b. I can subtract 18x from both sides, and just for practice sake, right, we really need this x term first, constant term second, which is positive, divide everything by -2, suddenly the signs change, and this becomes y equals 9x minus 13, right? So there's that linear thing. A lot of these have been yeses lately. And then number 24, number 24, notice that term on the other side that says 9xy. 2x plus 3y equals 9 times x times y. That product of those two dispels the linearity possibility of this. This alone tells you a no. You can try and get it in the form, but ultimately when you subtract 2x and divide both sides by 3, there's going to be a y on the other side of the equation that cannot join with the other y without having an x in the denominator of your equation. This is some form of a rational function or something of that sort. This is not a linear function because of that thing right there. Okay, number 25. Which of the following equations do not represent linear functions? Explain. Well, we just did a whole set of them. I don't know if I'm really down for a full verbal explanation of them, so I'm going to write the letters and say them out loud. In these cases here, x and y both being squared totally represents not a linear function, so which don't represent? This does not represent a linear function. In fact, this represents what's called the equation of an ellipse. This isn't even a function. You know how I stated most equations here will be functions? This one's actually not. This is a non-function and non-linear. This is called an ellipse. It kind of looks like this. Like an oval to you. Looks like an oval. This one, if I add x over, should be good. That can be in that form. It would be linear, therefore it's not a correct answer. X equals 8. Now, you might not know... Here, okay, hold on. I'm going to write x equals 8 on here, and let's talk about that a little bit. Remember, we're talking about the form y equals mx plus b, right? Well, maybe I subtract x to both sides of the equation, get that x and b on the same side. Now, it says 0 equals negative x plus 8. Where's y? Where's y? Y's gone. You might say, well, we had one where x was gone in an equation, and that was okay. We could have a linear function because x multiplied by 0. M was 0. You're right. M multiplied by 0. But the equation y equals mx plus b, where is it? The equation y equals mx plus b, y ain't multiplying with nothing except 1 or whatever other constant you want to put in front of there that's not 0. Y is multiplied by 1. It's not multiplied by 0. You need the y there. You do need y in this equation. You might not need x, but you need y. What's the difference? Not in this equation can you tell very much with it, but the original they had, x equals 8. X equals 8 is a vertical line. X equals 8 is a vertical line. And we found that vertical lines are not linear functions. They're linear. It's linear. It's not a function. So, it's a correct answer. X equals 9 minus 3/4 y. y is not multiplied by 1 here. Yeah, but the y exists, and we can divide both sides by negative 3/4. We can get this in y equals mx plus b form if you do the work. You got to subtract 9 from both sides and divide both sides by negative 3/4, or multiply both sides by negative 4/3. You can get to the equation. I'm going to leave it as it is because we've done so many of those, but those can't be written in the form y equals mx plus b. Or excuse me, this can be written in the form, therefore it's not correct. Y equals 5x over 11. So y equals, I'm just kind of using this as scratch work, 5x over 11. For y equals mx plus b form, this is the same thing as y equals 5/11 times x plus 0. There's another plus 0 waiting in the wings. And just because x is on top doesn't mean we can't write it off to the side, right? 1/2 times x is the same thing as x over 2, things like that, whichever way you want to write it. So you can write it off to the side. This can be your m times x plus b. Yeah, this is totally slope-intercept form, which means not a right answer. And then f, we saw a radical before. Square root of x is no good for linear stuff. That's not a linear function, which means it's a correct answer here. So which ones do not represent linear functions? A, C, and F do not represent linear functions. They cannot be written in the form y equals mx plus b. Whereas B, D, and E can. Number 26, fill in the table so it represents a linear function. Interesting. So let's first copy the table. Interesting because we have this gap in between all these things here, and I don't want to play trial and error. As much as I want to do algebraically, I'm going to attempt to. So follow along with what Mr. Robinson does here, shall we? First of all, confirm that your x's are increasing by a constant amount. I would say yes, indeedy. We're adding 5 each time. So far so good when it comes to saying as long as these increase by a constant amount, we want y to increase by a constant amount. Instead of guessing and checking until you find something that works, let's do something algebraically. Let's add a common difference. Let's just call it d. D, 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 and D. We have this number -1, and then we add d 1, 2, 3, 4 times. We add 4 d's to this, and we end up getting 11. Let's solve for d. Add 1 to both sides, and we get 4 times d equals 12. Divide both sides by 4, and you get d equals 3. D equals 3. If 3 is your common difference there, plus 3, plus 3, plus 3, plus 3, then that means -1 plus 3 gives us 2. 2 plus 3 gives us 5. 5 plus 3 gives us 8. 8 plus 3 gives us 11. That's confirmed. These are the three values, 2, 5, and 8 that would go here. Now, you're like, oh, Mr. Robinson, I had a guess and check, and I got that. Congratulations, right? That's not the point of the problem, though, right? We want to know how to do things algebraically, especially when it didn't have to be integer values. Could have been fractions, could have been tough fractions, could have been radicals, right? Probably not radicals. But in that case there, you want to do something that you know is a foolproof method. What if the numbers are big? What if they're obscure? What if these are decimals in and of themselves? You don't want to try something that's going to be very hard to determine. So you want a system that's going to help you no matter what. And that was going to be it. In exercises 27 and 28, find the domain of the function represented by the graph. Determine whether the domain is discrete or continuous. Explain. Now, they're not asking for range. They're not asking for range. Now, number 27, I can tell you straight off the bat, which is, I feel like the book's doing something out of order again. I felt like that the fact that we did domain and range we're not doing range here, but the fact that we did domain and range in section 3.1 and not knowing the words discrete or continuous, but we were okay to do it there, means we should be able to do it here. But I had described discrete and continuous at the time to let you know what we were doing and why we did the way we did. My point is, I don't want to write the domain, then tell whether it's discrete or continuous. Based on it being discrete or continuous, I should know what kind of domain I'm going to write. Number 27 is discrete. It's discrete because the points aren't connected. They're finite, and I can write them as a list. That's why. So if it's discrete, that's why I know I can write as a list. So the domain is going to be, now notice here, first of all, domain is your x values, okay? Also, these x values are increasing by amounts of 2. X here is 2, and this is 4, and this is 6. And those are the values for which points exist on this graph. 2, 6 is a point, 4, 12 is a point, 6, 18 is a point. But the domain are your input values. So x equals 2, x equals 4, x equals 6. Those are the three values that exist. Write in increasing order, avoid duplicates, no problem. 2, 4, 6. It says explain. I think they're explaining why it's discrete. The points are separated. I can write them as a list. Number 28, on the other hand, you can't lift the pencil off the paper without connecting all infinite numbers of points. That would make it continuous. It's continuous. The graph is a line segment. It's all connected. The points are connected, and it's not just these 2 points. It's every single point. There are points all over the place right here. I can't write them all as a list. Instead, I write a compound inequality. And remember, we're just doing the x values. We're going from x equals apparently 0 all the way to x equals, looks like 7. These are now going by ones again. So we're going from 0 to 7. I don't know why we're not doing range. But the domain here goes from 0 to 7 on x, and it includes 0 and 7, and every point in between. No point is missed. It's not just 1, 2, 3, 4, 5, 6, 7, which, by the way, it does hit 1 right here, and it does hit 2 right here, etc. So there's that. I mean, I know the section has been avoiding talking about range. I just don't know why. I should be able to know, but I don't know. 29 to 32, just to determine whether the domain is discrete or continuous, explain. Now, they don't actually list out the domain. Well, they kind of do, but you have to identify them. The domain here goes from 2 to 6 like that, but these could pick out specific parts. These ones didn't have any context to the questions. These ones do. This says input is the number of bags that you have. Output is the number of marbles that you have. To me, the argument is you either have a bag or you don't. You have a bag of marbles or you don't. Okay? So if you do or don't, in that case, that's a discrete relation. So number 29, this domain is discrete because each number of bags is a whole number. Number 30 says the number of years that go by and the height of the tree. Now remember, they are asking whether the domain is discrete or continuous, but then I think that would mean the range, therefore, would be discrete or continuous. Input in years, year 1, year 2, year 3, here's the tree height in feet. Now, can you have half of a year, especially half of a year where the Y changes height, where the tree changes height? Yeah. It can change height in the next day, change height in the next second. Little micro fractions of heights, right? Things that we can't perceive. It might even shrink. The point is, at every instance of time, and normally time is continuous, not always, just like normally time is an input variable. Normally time is continuous, and this happens to be one of those things. This is continuous because time can be separated into any amounts of fractions. The number of years, do we have to do the domain? No, but the number of years can be quantified fractionally. I think if you write that, I think if you're an 8th grader doing an IM1 book and you have to submit your homework that your teacher's grading and you write this straight up, your teacher's going to say, what are you doing? So that's me, a math teacher or whatever, an experienced 36-year-old individual stating some words there that I don't think your teacher's going to say, who did you copy off of? And if your classmate wrote the same thing. So please don't copy my work. That's partially why I sometimes don't write things. Number 1, I'm lazy. Number 2, we have to invent for ourselves sometimes, right? Normally I write everything, but this is a solution guide. I just want to make sure you understand what I state. Spin it in your own words. Have ChatGPT do it for you. I don't care. This one here, input time in hours and output in distance and miles. Maybe you're driving. You're likely driving. Looks like 50 miles per hour here as you're going. It's linear, but it appears to be continuous as well. Once again, it's time. Time can go on in a fractional way. I'm going to say the same thing here as I said here, only change years to hours. Hours can be quantified fractionally. You can have minutes, you can have seconds for which you're changing distance. And that's likely what's going to happen, right? We don't teleport. We don't go from here to in a matter of moments. And even if we did, we can identify ourselves at any distance marker at any time. Number 32, the input is relay teams, X, and output is number of athletes, Y. You have no relay teams, you have no athletes. One relay team is 4. Unless you argue that you can increase the number of athletes, and we're not a team, and whatever, this would be considered to be discrete. Okay, there's no fractional numbers of teams. It must be a whole number. Discrete. The number of teams must be whole. 0, 1, 2, 3, 4, etc. Okay, in exercises 33 and 34, describe and correct the error in the statement about the domain. Here they said 2.5 is in the domain. Now, I would agree with them if this graph was connected. If you had a connected graph, you had a continuous relation here or function, then you could say when x is 2.5, you get a value here for y, therefore it's a point. But this here you can tell is not a point. It seems to be conspicuously absent. It is not in the domain on number 33. There is no point. Not that there's no reason. There is no actual xy value there. There does not exist a point when x equals 2.5. Therefore, 2.5 is not in the domain. It's all about x in that case. Range is all about y. What's in the domain? 1, 2, 3, 4, 5, and 6. And that's it. Number 34, it says the graph ends at x equals 6. True. So the domain is discrete. Not true. And I think I get what they're saying there, because this is a mistake people can make. Sometimes people don't really know what discrete means, so they go by the opposite. Because, listen, you can't be both discrete and continuous at the same time. So you might be asking, well, I guess arguably you could, but if you're both, then you are continuous. Sometimes people are like, well, I don't know what discrete means, but I know what continuous means, so if it's not continuous, then it must be discrete. And then they say this is not continuous, and I say, why is it not continuous? They say because it doesn't go on forever. That's not what continuous means. That's what continual means. Never ending. Continuous means never disconnected, if that makes sense. Now, you could have a graph that separates itself like that, and then it joins up again and does something like that. I guess this would be an open circle. And that would still be, I mean, it's discontinuous as far as the jump goes, but it's continuous as far as infinite set of points in between. When I write my domain, it needs to be a compound inequality. So this is definitely not discrete. It's definitely continuous. The graph ending has nothing to do with continuity. Only continualness or whatever. This graph has connected points, an infinite set of connected points. Therefore, it is continuous and not discrete. Again, continuous and continual are not synonymous with each other. You could have a discrete graph that's actually continual. You could have points never ending that go on. Maybe there's no way to indicate that. Like, I don't know how to draw an arrow there to say it keeps going like that pattern. But you can have a continual discrete graph and a continuous non-continual graph. Ending, finite bounds. There's that. Okay, number 35. Modeling with mathematics. The linear function, and it is linear, m equals 55 minus 8.5b, represents the amount m in dollars of money that you have after buying b books. Okay, now before I continue on this problem, this m and this b has nothing to do with the y equals mx plus b. In fact, you could actually argue that this is a version of an m and this is a version of a b for y equals mx plus b form if this were y and this were x. They have different letters, I guess, to indicate b books and m money. They probably should have put d for dollars, but m money. So money and books, okay? The amount of money you have after buying b books. The more books you buy, less money you have. Find the domain of the function. Is the domain discrete or continuous? Explain. Now, I want to state whether it's discrete or continuous first, right? You either buy a book or you don't. So that sounds discrete, right? That's how I wanted to describe it that way. Now, finding the domain's a different story, but you either buy a book or you don't. Therefore, it is continuous. Books must be purchased in whole number amounts. Now, they said find the domain. Now, this might have to do with making a table. They did say graph the function, so we're going to have to probably make a table anyway. The reason I have to make a table is because I have to figure out how many books I can afford. If you understand, and you may or may not here, the 55 there represents the amount of money you start with. And we will make sense of that when we start off this discrete set. These inputs are b. The amount of money you have depends on the number of books, so let's substitute values for b. Let's start with 0, not buying a single book. 55 minus 0 is 55. That's where it says you start with $55. Now you buy a book. You take away $8.50 from there. Now you have $46.50. I'll put $46.50. We'll put it in terms of money. 2, you have, and listen, we can play this all day long, plugging these numbers in. I'm going to do this in kind of a faster way on my calculator just to kind of get it done. You can always plug in the numbers, 55 minus 8.5 times 2, etc. I want to show you kind of how this thing carries on forward, though. Oh, my calculator's not operating right now. It's being dumb, so never mind, forget it. Let's just keep going. Subtract another 850 right here. That was me being lazy anyway. You would get, what, $38? When it's 3, you have $29.50. 4 books, you'd have $21. 5, you'd have $12.50. And 6, you'd have $4. Can you purchase a 7th book? No, you'd be left with $4. You can't buy another book unless there's a cheaper one available, but there's no reason to see that it is. So that's the relationship. Now, what is the domain? The domain is the number of books you can possibly buy. Not just 6, but up to 6. So your domain is the list of values. 0, 1, 2, 3, 4, 5, and 6. The range is a different set. How much money you'll have left. That's a different set. They say graph the function. I have this blank space to do that. So here comes our graph paper, guys. I'm going to copy and paste this. I will provide this for you, of course. I only need the first quadrant. It's only positive values. And we go up to 55. Gets a little tricky as far as the points that I want to kind of use here, because I don't want to go by amounts of 11 or anything like that. Here's what I'm going to do. I am going to go by amounts of increments of 5 on y. X is simply going to go up by 1s. And we're just going to have to understand that this point will go a little bit off the edge for this one. So this is actually 50, and this is 25, etc. Whereas, and again, I don't need any of this, but X is going up by 1s. So when X is 0, B, this is B, this is M. And when B is 0, M is 55. So if these are going up by 5s, 40, 45, 50, 55 is a little bit off the graph like that, but we're going to have to deal. After one book, it's 46.50. Now 45 is right here, 50 is right here. 46.50 is a little closer to 45 than it is to 50. So I'm going to kind of plot it right there. I'm going to do the best I can with these ones. And remember, we don't connect the dots. It's a discrete relation. At x equals 2, we have 38. Here's 25, 30, 35, 40. 38 is 3/5 of the way between 35 and 40. Then 29.50. That's awfully close to 30. Just a tick underneath. Probably something you can't even tell when x is 3. Can you tell it's slightly under? Maybe. When x is 4, y is 21. That's a little more than slightly off now. You can probably tell a little bit more that maybe that's a 21. When x is 5, y is 12.50. Now, this is 5, 10, 15. 12.50 is exactly halfway between 10 and 15. And when x is 6, y is 4, which is 4/5 up the way from 5. The same distance as 1 would be from, as 21 would be from 20. So there's that. And that looks like if I did draw a line, then I could, but remember, it's not, it's linear, it's just discrete. So there's the graph using the domain, and we have it. Okay, number 36, modeling with mathematics. The number y of calories burned after x hours of rock climbing is represented by the linear function y equals 650x. They state, find the domain. Is it discrete or continuous? Explain. Once again, it makes more sense to talk about whether it's continuous versus discrete before we find said domain. In this case here, you're burning calories after what? X hours of rock climbing. It's not just you either climb for an hour or you don't. You can climb for 2 minutes and say, this ain't for me, and burn a calorie along the way. You know what I mean? Burn a couple calories along the way. So with this one here, it's a continuous relation. You can burn fractional amounts of calories, and time can be, fractionalized. So this is continuous. This is continuous. And if it's continuous, that means its domain is represented differently, either as all real numbers or an inequality or compound inequality. Now, there's no limit to the number of hours you can rock climb. Have at it. You just can't rock climb for negative amounts of time. And you start at 0. Either you climb rocks and burn calories or you don't. And that's okay. You don't have to. So as far as this goes for your domain, x can be 0, but it can be greater than. So greater than or equal to 0, that's the number of hours that you can rock climb. Any fractional amount. So there's the continuous, there's the domain. That is part A. Part B. Graph the function using its domain. Now, there are only so many points that we can plot, especially since y equals 650 times x. In this same vein, we will be doing a table and choose values that are kind to yourself. Even though it's continuous, we'll just connect the dots after. So if I do 0, 1, 2, 3, and 4, I guess that's a lot of hours to rock climb. I haven't actually done it. You climb for 0 hours, you burn 0 calories. You climb for 1 hour, 650 times 1 is 650. And we go up by amounts of 650. If you were curious on the previous question how I was calculating these things in my head so quickly, I was not doing 55 minus 8.5 times 3 to get this number. I subtracted another 8.5 from this number in my head. So that's how I actually got those numbers. Same thing here. You can do 650 times 2. It's pretty bare bones, but I can also add 650 and I get 1,300 calories burned. And then here, 1950 plus 600 here is 2,600. So it goes up by quite a bit. I might leave out the 4 when it comes to fitting on the graph, unless I can decide better values that I'd prefer to plot in this thing. But, you know, we're going to use this scaled graph thing again. So let's see. X's can easily go up by 1s. That's all good. Y's, if I have 1950, what if I make this instead 2,000? 2,000, which means these are going up by what? 200s? This is 1,000. So 200, 400, 600, 800, 1,000, etc. So if they're going up by 200s, we're not going to be able to fit the 2,600 unless you kind of shoot way up here and pretend. But we can do what we can here. 0, 0. 1 comma 650. So this is 200, 400, 600, 800. 650 is a quarter of the way up from 600 to 800. 2 hours in is 1,300. 1,000, 1,200, 1,400. 1,300 is right in between there. 1950, this is 1,800, and this is 2,000. 1950 is 3/4 of the way up between 1850 and 2,000. And if you wanted to try it, at 4 would be another 200, 400, 600. Let's see how close I was in actually getting 2,600 there as we connect the dots. And not only that, our line will feature an arrow because this can keep going. The domain goes toward any positive numbers. Looks like my 2,600 is not bad. In fact, my starting part is actually bad. Let me try and fix that and see if that fixes the rest. That's actually pretty good. So I kind of got my 2,600 there. I like it. They're hard to see now, but that's my line that represents not only those points, right? We're burning calories throughout the entire first hour up till 650. It's not like you magically burn the 650 like that. It has to increase over time. Number 37, modeling with mathematics. You are researching the speed of sound waves in dry air at 86 degrees Fahrenheit. The table shows the distances d in miles. Sound waves travel in t seconds. So you see this table. I'm going to copy and paste it so I can mark this up a little better with my stylus. Okay, let's see what's going on here. I'll leave this over to the side. All right. It says, does the situation represent a linear function? Explain. What we need to check here and see is if this has a constant increase. I'm more inclined to use my calculator at this point, but after seeing what the first two have, I think I'm recognizing what's going on. Maybe it does, maybe it doesn't. Let's see if they don't fool us here. We're adding 2 seconds each time here. Doesn't mean it's not continuous or anything, but just as this has a constant increase of 2 on time, distance would also need a constant increase. I don't know if you can tell, but this is 0.434 plus 0.434. And I wonder if this is plus 0.434 as well. Right now, it looks like this thing's having a constant increase of some sort. If not, we probably couldn't do all the rest of the stuff. But plus 0.434, you betcha. Now, if you ever had to figure out what it was, do one number minus the other. Use your calculator as well if you need to. And it would be mean if they did like, haha, this is plus 0.433 on this one, you idiot. Why didn't you try this last one? If this one's not plus 0.434, they're just mean on the problem. I think that was plus 0.434. All right, so is this a linear function? Explain. Yes, it is. Linear because constant rate of change on both x and y. Rate of change on x and y. As shown, C to the right. C to the right. Part B, find the domain of the function. Is the domain discrete or continuous? Explain. Well, this is time. Let's see it again. You're researching the speed of sound waves in dry air at 86 degrees Fahrenheit. This shows the distances sound waves travel in t seconds. So we measured these things here, but it's totally continuous. There's a 1 second mark and a 0 second mark and a fraction of a second mark and things like that, that the sound can travel over that time. Again, time generally not only represents inputs, but also continuous relations, or functions in this case. This is continuous because time can be any value, including fractional values. Now that time isn't negative as far as we're not looking in reverse in time. So when it comes to the actual domain itself, positive numbers are 0. The domain here is time can be greater than or equal to 0. So despite the fact that we have some nice points there, they don't represent all the different times we can have. Part C does say graph the function using its domain. Well, graph the function using its points is what we need, but I think we have to fit all these within our domain. So I still have that table on the left side there, so I hope you can still see it and understand where I'm coming from. Now the y values are definitely going to have to change their scale in a different way, and I'm thinking about doing the same things I did in the last one. Bring this all the way up to 2 something. Last time was 2,000. Now I think here I'm just going to make it 2. And this is going to be 1. Even though the last one will kind of fall off the edge. You can think of this as thousands, though, if that helps you. So, like, if you don't know where 0.434 is, think of this as like 1,000 and think of where 434 is. So you still go up by like 200s, if you will. So kind of think of it like that, okay? So x's are going, here's 2, 4, 6, 8, 10. So you have to be careful here. When x is 2, y is 0.434. So think of 200, 400, here's 600. 434 is even still like not even 450 or what have you. It's not even a quarter of the way, so probably about there, 0.434. Looks like that. Oh, that's when x is, excuse me, that's when x is, oh yeah. Okay, that's when x is 2. When x is 4, it's 0.868. So like 868, 600, 800, 1,000. Here's 900. 868's less than that, so it'd be about right there. And I'm not labeling the points. You see where they are. Hopefully you can recognize it. When x is 6, y is 1,302. You're not going to be able to differentiate 1,300 versus 1,302. So 1,200, 1,400, 1,302 is it's virtually halfway in between. Again, we won't be able to differentiate that with such a small scale. And yes, I know these aren't actually hundreds. This is just me saying them out loud. It helps me too. When x is 8, y is 1,736. 1,200, 1,400, 1,600, 1,800. 1,700 is in between. 1,736 is closer to 1,750, almost 3/4 of the way up like that. And then the next one, 2,170, when x is 10. Here's 2,000. And I guess this would be 2,200, right? So 2,170, just a tick below. Not even, kind of like that. Now they did say graph using the domain. We graphed the points that we had, but the domain is greater than or equal to 0. That means that it starts from 0 onward. Now we didn't plug in a point for 0, but you can imagine no time means no distance sound will travel. That means there's a point 0, 0, or better yet, that's where we're going to start from. If you didn't know that, when you started graphing this line, use a ruler, by the way, and draw it, you're going to find that it goes through 0, 0 like that. This goes onwards and upwards and continually, as well as continuously. So draw an arrow at the end. I do have an arrow feature. Do not draw an arrow at this end. But it starts at 0 and moves onward. And that is our graph. Okay, number 38. Modeling with mathematics. The function y equals 30 plus 5x represents the cost y in dollars of having your dog groomed and buying x extra services. So to me, when I hear that, again, as far as interpretation goes, I'm thinking that it costs $30 to have my dog groomed. And then I spend $5 per service, per extra service here in this set. You can also rewrite this as y equals 5x plus 30. Up to. Here are the different kinds of extra grooming services. Oh, you get your dog's nail polished. There we go. Part A, does this situation represent a linear function? Explain. Oh, by the way, I was just mentioning how we could rewrite it in that other form. Let's go ahead and do that. Y equals 5x plus 30. So is it a linear function? Yes. Let me write linear this time. Linear. Reason I got it in y equals mx plus b form. There we go. Part B. Find the domain of the function. Is the domain discrete or continuous? Explain. Well, you won't have half of a service. Can you only treat one of the ears? Can you only treat half of each ear? Can I just pay $2.50 for that? Can you just get this one nail polish? No, hold on. What's the thing that the kids do these days? These 3 nails polished, but not that one. And I only pay $4 instead of $5. Can we have that? No. You either get the service or you don't. So this would be a discrete function. This one's discrete because each service is represented as a whole amount. No fractional services here. Sorry to disappoint. Part C, graph the function using its domain. Well, we still have to get some of the points out for this thing, right? Now let's make this one as a table. Now there are, listen, the domain, did they ask for the domain yet? Oh, they said find the domain of the function. I'm sorry. Let's do this first. So domain, it's limited. It's not only discrete, it's limited. There are only 5 services that I see here. Now you can choose to get none of the services, or just pod treatment, or just nail polish, whatever, or deshed and do whatever. So 2, 3, 4, and up to 5. There aren't 6 of them. You don't brush their teeth twice at a time and say, all right, and there's, or if you do, we're only counting it once. That's your domain. Now we're going to graph using the domain, which means we might need to create a table. And it's discrete. Keep that in mind. So 0, 1, 2, 3, 4, and 5. Now the equation was y equals, I'm going to call it 5x plus 30 or 30 plus 5x. 5 times 0 plus 30 is 30. 5 times 1 plus 30 is 35. And you're going to see a constant increase here of 5. Once you recognize that pattern, you might want to utilize that. And listen, over time, I already said this probably before, but within the chapter, we're probably going to recognize more and more as to how we can do that without literally plugging the values in and just use that. You probably have caught on, which is a good thing if so. You learn as you go. Anyway, we got to graph this. Right? So for this one, it's discrete, so we won't connect points. We have to go up to 55. That's one of my versions of saying 55 is just but 5 more than 50. So if I capped this off at 50, then I could get perfect increments of 5 here. We might have done something like that before. So when x is 0, y is 30. When x is 1, y is 35. 35 and 40 and 45 and 50. And I can count all the way to 55. There it is. Now, I'm not labeling the points, but if you'd like to, go ahead. But those are the ones that I have represented for this. You do not connect the dots. This is your domain. Straight up. We're all good. They're not asking about ranges, but the ranges are based on those domains. Okay. Number 39 to 42. Write a real-life problem to fit the data shown in the graph. Determine whether the domain of the function is discrete or continuous. Explain. Now I feel kind of, well, first of all, I could tell you, you could probably say discrete or continuous on each of these. I did the lecture portion, and I came up with one on my own at the time, and now that's one less creative thing that I can think of now that I have to think of these ones. So I apologize if I pause, not literally, but if I pause in time thinking about trying to be creative with them. You really don't have to, but come up with something that if it's discrete will for sure be discrete, and if it's continuous will for sure be continuous, and applies to the numbers that we see here in context. So on number 39, we have this graph, which by the way is discrete. I don't know why they need me to explain. Well, is this the first time we're looking at discrete and continuous on a graph? If so, discrete, separated points, that's what I'm telling you out loud. So as far as discrete goes, we have to jump from 0 to 4 on something, and then from 4 to 8 on something as y increases by 1. So that's something I have to think about. They did have one, and maybe this is cheating. They did the relay thing, the relay teams, or whatever they called them. I can do the same thing for a group, right? I can say 4 people make a group. Four, how about students? 4 students make a group. You know, you can't have less. And that's kind of it. Every time we, another 4 students come together, a new group is formed. Now that's important for the new group part because that means that there's one group from 4 students, and 8 students makes 2 groups and things like that. 0 students would make 0 groups, and there's something like that we can use. Okay, number 40. Now this is an interesting one because it's also one of the first times that we're seeing negative values of y, as well as, there's continuous, all that kind of stuff. So first of all, it is continuous. We're connecting the dots. It's not continual, but it's continuous. It goes from 0 to 6 on x. X spans right here from 0 to 6. Y goes as low as -1 and as high as 2. So we have to find a way of decreasing something over time into negative land. I can think of something that, like, you know, if like water is surface level, then we can go underwater as well as time goes on. I don't know how we can slowly go underwater like this. Planes, for example, won't go underwater. We can do something like, what else goes to negative territory? Like, you know, you can go into debt with money. We can think of temperature. Let's do temperature. Let's do hours, and let's do degrees. Let's do degrees Celsius. That would be a little bit better than degrees Fahrenheit. Let's say we're freezing a water bottle or something like that, or a steak or whatever. You know, I don't know how slowly these things would go into play. Well, it depends on the temperature of the freezer. So I could say, I'm going to talk about steak, okay? You are freezing a steak. Should we do hours? Let's see. That's very little change, but you are freezing a steak, a streak. You're freezing a steak, and I'll just say every minute, the steak. Well, here's the thing. I don't know how much we need to talk about rates, but because it's linear, there's a rate of change here. Every time another 2 minutes passes by, the steak freezes another degree. It gets another degree colder. Another 2 minutes, another degree colder. Another 2 minutes, another degree colder. So that's going to be my explanation of this. Every 2 minutes that passes, the steak freezes, the streak. I keep saying streak. The steak freezes another 1 degree, I'll say Celsius, because otherwise that's got some burn on your steak otherwise. 0 degrees Celsius is freezing point, so getting below freezing point right there is pretty good. All right, number 41, also continuous and already begins in negative land. So this time I really want to change it up and think about like water or something like that, right, as we're changing something. So on number 41, first of all, it is continuous. Whoops. We can talk about water. We can talk about money. I can always think about those kinds of things. Where we're underwater, where we're in debt. You know what? I don't want to do money because money isn't completely fractional. You can get down to a penny and that's it. I guess you can like stock value and stuff maybe. But let's talk about like water. 300 feet of depth below sea level, for example, or underwater. And then after 30 minutes, you rise to the top. So you are snorkeling. You are in a submarine. In a submarine. 300 feet below water or underwater, and making a descent, or making an ascent at, so check this out. These scales for Y are going by 50s. So this is 50 feet every, I don't know how fast they go up. 50 feet every 5 seconds is too much. So how about every 5 minutes? So you don't get whatever that's called. 50 feet every 5 minutes, which by the way would reduce to, because we're going to talk about this stuff later, that's 10 feet per minute. 10 feet every minute, so a slow ascent of that up until, oh, and by the way, I should have said that for the steak, up until the 6th minute. Up until the 6th minute. Now for this one here's up until the 10, 20, 30th minute. You reach the surface after 30 minutes. I don't know if I'm over-explaining that, but we have to do it within our domain as well. It's not just about rate, and it's not just about situation. It's about domain as well. It's not just about continuous and discrete. Okay, number 42. Number 42. We actually don't start at 0, 0. So that's an interesting thing here. Now these scale by 5s and these scale by 2s. X scales by 2s. When X is 2, Y is 0. When X is 4, Y is 10, etc. And this is discrete. I'm going to have to think about this one because you need something that when X is already 2. It can be the 2-hour mark of something, but normally time isn't discrete. Now, that's hard to come up with a time scenario that is discrete. You want something here where you already have, the problem is these go by 2s. I need to make something that goes by 2s here. 10, Let me pause and think about one of these because I don't want to sit in this video and just have you watch me stew over it. So the main two things I'm struggling with, and I'm going to come up with something soon, but everything I'm thinking of either would start at 0, 0, or it's hard to go in pairs. That's the problem. So now I'm going to think of pairs. When I think of pairs, I was first thinking of like hitting a double in baseball or something like that. I'm thinking of things you purchase. You might pairs of shoes, pairs of socks, pairs of gloves, pairs of I don't know, something like that. So something you wouldn't only buy as once, because before I was trying to do things where like every 2 times you score a basket that this happens, but what about that basket you scored in between, right? Every 2 videos that you make, but what about the video in between? So I have to think of pairs of things. So I'm going to talk about like buying pairs of socks, but we need to find it in a way that the first 2 pairs of socks you buy are free or that you stole them, but we can't be talking illegal things on here, right? Not being criminal. So something like you buy every pair of socks you purchase costs another $10. Now, by pair, X is the number of socks, right? But the first pair of socks is free with any purchase. How about that? So being free with any purchase would also, I guess, see, the only problem is zero pairs of socks purchased is also $0. I can't find a way to make it 0. Sometimes you have to force limitation. So for example, you must buy a pair, right? You must buy 2 socks in this situation. You can buy you can afford, well, I have to talk about domain. You can buy up to 10 socks. They have to purchased in pairs. That means 5 pairs of socks, but that way the X's are 10s and the Y, etc. Okay. That one's kind of harder to come up with, and yeah, you have to be creative. Maybe you have to use mine. I'm not sure. Okay, number 43, using structure. The table shows your earnings Y in dollars for working X hours. Does it now? What is the missing Y value that makes the table represent a linear function? Okay, so this one, despite the problem that we did previously, where we did this whole like guess thing, which you can do, you can also work off of what you see here. I see the change from here, and this needs to be constant this way. So we can say, hey, 71, I'm just going to write it over here. So for part A, 7140 minus 6120 gives you however much you add from 6120 to get 7140. And that's going to be $10. Is this money? $10 and I think 20 cents. $10.20. So if we're adding 1020 to get from here to here, then 6120 minus 1020 can get us that number, or 4080 plus 1020 can get us that value, which is $51. 51. So what's the value that goes here? It's 51. It says, what is your hourly pay rate? Now that's actually what I had to answer for this part here, right? So my pay rate is $10.20 per hour. So I kind of had to answer that one first. Not necessarily. You would have had to know what to do, but this could be a midpoint between these two numbers, meaning you could average them and not come up with that 1020 to make that so. Or you could have done what we did before. 4080 plus 2D equals 6120, and then do the subtract and divide. Maybe you wouldn't have actually come up with, that would have come up with the 1020 that way. So, yeah, that's it. Number 44, making an argument. The linear function d equals 50t represents the d distance in miles car A is from a car rental store after t hours. So I got to update. Cross-device experience host just got updated. I don't know what that is. What was I talking about? So this is saying after you rent a car, you're zoom driving away from here. It says the table shows the distances car B is from the rental store. Oh, car A uses D equals 50t. Car B uses Carvana. Car B uses this guy. That's setup. Does the table represent a linear or nonlinear function? Explain. Well, this is a constant rate of change from 1 to 3 to 5. You might not start from 0 to make it happen, but those are adding 2. This one adds 120 and then this one adds 130. No, part A, B is not linear, is non-linear. Distance isn't constant, as time is. Okay. Part B, your friend claims car B is moving at a faster rate. Is your friend correct? Explain. Well, 50t to me means, well, here, look, you can do this. We can create a table. For hour 1, 3, and 5, where would A be at here? I kind of need room. I'm gonna do this one more time. So here's car B's distances. Car A's distances could be here. 50 times 1 is 50. 50 times 3 is 150. 50 times 5 is 250. So B is traveling more distance at equal time than A travels in comparison. Your friend claims car B is moving at a faster rate. Your friend is correct. So part B, my friend is correct. Car B covers more distance over the same amount of time compared to car A. All right. Now, I actually found those distances on car A right there. Okay. At least for those hour marks. Number 45. Mathematical connections. In exercises 45 to 48, tell whether the volume of the solid is a linear or nonlinear function of the missing dimensions. Explain. I guess what they're asking is, when you set this thing up, now volume of a prism is length times width times height. So volume is going to be S times 9. And it says when it comes to solving for S, or coming up with what remains and what you don't know, is that represented linearly? As in, like, this is y equals mx plus b. Well, S times S is S squared. This becomes 9s squared. That is nonlinear. That can't be written in y equals mx plus b form or v equals ms plus b form, whatever you want to say. It's nonlinear because this is squared. Number 46, the volume of a triangular prism, area of base times height. We need 1/2 area of base. Sorry, 1/2 base times height of the, to get the area of the base, times the height right here, which would be 4. So the volume here is 1/2 base times height of the triangular base times the height of the prism, 4. Half of 4 is 2. 2 times 3 is 6. This is volume equals 6 times b. B being that independent variable, this is like your y equals mx plus b form, plus 0, if you will. You don't really need the 0. But this is linear. This is linear. This is to the first power, separate from your volume, all that kind of stuff. We're totally good there. Now, if you want to put the plus 0 to make it that form, go ahead. It looks like that y equals mx plus b to me. Oh, that was 46. Forgot to move it over. Number 47, we have a cylinder. Now, I don't know how many of these formulas you're actually supposed to know, so these can be challenging bits if you're not sure. But volume of this one, you get area of base times height. Now, this area is a circle, pi r squared. So pi, your radius is 2, pi r squared, times your unknown height. Now, this is 2 squared is 4. This is 4 pi times h. Believe it or not, pi is not a variable. It is a constant, and h is to the first power, so is v. This could be plus 0. Y equals mx plus b. M could be 4 pi. All that kind of stuff. This is totally linear. We're all good in this case. We're all good in this case. Number 48, we have a cone. Cone is 1/3 the area of base times height, and this time our radius is unknown, which is probably a problem here. This is 1/3 pi r squared, and literally r, we don't know what it is yet, times a height of 15. When we simplify this, 15 divided by 3 is 5, and we get 5 pi r squared. R being this variable in a quadratic sense, because like number 45, in the same way, this thing makes it non-linear. Non-linear. When graphed with r and v in the way, it's going to be quadratic. Number 49. Reasoning. A water company fills 2 different sized jugs. The first jug can hold X gallons of water. The second jug can hold Y gallons of water. The company fills A jugs of the first size and B jugs of the second size. What does each expression represent? Does each expression represent a set of discrete or continuous values? I don't know if there's any of them that would be discrete. I'd have to, oh, except for B. Okay, hold on. All right, so I gave something away. All right, X plus Y. X plus Y itself, first jug can hold X gallons, second jug can hold Y gallons. This is how much water one jug of each type can hold. What do they call them? First jug and second jug? So X plus Y represents gallons. Gallons of water held by one of each jug. That is continuous in that, you know, there's like a constant flow of like how much water you can put in versus not, that kind of thing. We're talking about gallons. Gallons is continuous when we're talking about fluidity of this. So anything that's going to involve water in that way is continuous because of however much you're holding on there, right? Part B says it fills A jugs of the first size and B jugs of the second size. A plus B is a number of jugs amount. Number of jugs of each type. How many there are. That's discrete. It's whole number of jugs. Either you have the jug or you don't. I don't even know if they say whether water's filled in it. This is just discrete. Now the part I'm boxing's here. This part should be boxed as well, but it gets a little I stayed a little bit there. A times X represents, remember, this is number of jugs of water times the number of gallons in each jug. So this is number of gallons. This is amount of gallons of the first jug of A amounts of the first jug. That should be continuous. Now we're talking about gallons again. So we're back to continuous for that. And then AX plus BY, part D, is everything involved with that. The total gallons of water in all the jugs of both types. Whoops, that should be a Y. So AX plus BY, we're talking about number of gallons, total gallons, of both jugs. Let's see, of A amounts of first jug. Let's see, how do I say that more quickly? What did I say before? Of the water in both types of jugs. The company fills A jugs of the first size, B jugs of the second size, of all the water in both jugs. Also continuous. Hopefully, even if you're like, what's that word? I'm like, well, it's either continuous or discrete. Which one do you think it is? And then we have to go off of that. All right, number 50, thought-provoking. You go to a farmer's market to buy tomatoes. Graph a function that represents the cost of buying tomatoes. Explain your reasoning. Well, for each tomato you buy, it's probably a constant amount, right? I don't know how much tomatoes cost. I'm not good at that. Let's say 50 cents a tomato. I'm not good at it. I don't buy tomatoes from a farmer's market. So 50 cents a tomato, but you either buy this tomato or you don't, right? I talked about picking apples from a basket. You either pick the apple or you don't. They said graph it. So let's do kind of an XY there in the same way. Let's say 50 cents a tomato. I don't know if that's right. I'm just going to say it. I know tomatoes can be a hot commodity. You might not buy any tomatoes, or you might buy 1, 2, 3, 4. Let's just go up to 5. Zero monies, $0.50, $1, $1.50, $2, $2. I was gonna say 3, $2.50. Maybe there's a way of buying in bulk. Generally not the case at a market. Graph a function. It says explain your reasoning. My explanation will be first here. First of all, this is discrete. Either you buy the tomatoes or you don't. Buy whole amounts of tomatoes. Each tomato is a fixed cost of 50 cents each, and there are 5 tomatoes left. So you can buy up to 5 if you so choose, or none at all. And this is the different amounts that you'd be spending. It's still interesting that they just don't talk about range. Right? We've been already talking about range, and I know that domain's a portion of it, but they haven't said the word range at all yet. I mean, the amount of money you spend is your range, whereas this is your domain. So I'm going to scale these exactly as they are. So 0 tomatoes spent, $0 spent. 1 tomato purchased is 50 cents. 2 tomatoes is $1. 3 tomatoes is $1.50. 4 tomatoes is $2. 5 is $2.50, like that. You do not connect the dots, and you end at that point based off what I created. Most thought-provoking questions are open-ended, which is me deciding what I want to say with that. Okay, number 51. Is the function represented by the ordered pairs linear or nonlinear? Okay, this one's a little bit different because you know how I stated that x would have to increase by constant amounts for us to judge y? X here is not increased by constant amounts. So we're going to have to make for different kinds of ways to talk about what's happening here, right? Even if I did it in a table, we're not trying to see how much we're adding on y here each time, but we have to look for a constant rate. So the constant rate, we should probably ask ourselves, if it were linear, how much would we be increasing over just one interval of time and two, things like that. So for example, y here changes from 12, let's change color. Y here changes from 2 to 14. That's adding 12. Whereas x here changes from 0 to 3. That's adding 3. When we talk about rates, we talk about how much y changes versus how much x changes, right? It's like dollars per tomato, things like that. Now 12 divided by 3 is 4. That means every time x increasing by 1, if it were linear, it would go, 1, 6, and 2, 10, and 3, 14. It would add 4 each time. Does this happen in each other scenario? Now, I'm not willing to try everything under the sun, but I'm going to try from one to the next in the same way. Let's go from 14 to 22. That's an addition of 8. And 3 to 5, which is an addition of 2. As this increases by 8 on y, does x increase, and x increases by 2? That's a change of 4 for every one. Y increases by 4 every time. So that's the same so far. Let's keep going. Let's see if it ever breaks, I'll stop. If it continues, I'll keep going until there's no more. 22 plus 16 and 5 plus 4 gives us that, and 16 over 4 is also 4. Now this would just be mean if it doesn't work for the last one, but let's give it a shot. 38 plus 8 and 9 plus 2. 8 over 2 once again is 4. So based off what we see here, there's a linear relationship every time. And so I'm going to state linear. They said explain. This is a perfect time to do an explanation. This is linear because based on the changes in y and x from one point to another, there is a constant rate of change of 4 on y. Let's see. A change of 4 for y. 4 on y for every 1 for x. And that's just what's happening. I could fill out the rest of the table. 1, 6, 2, 10, 3, 14, 4, 18, 5, 22. And we're just adding 4 to y every time x increases by 1. Number 52, how do you see it? You and your friend go running. The graph shows the distances you and your friend run. Describe your run and your friend's run. Who runs at a constant rate? How do you know? Why might a person not run at a constant rate? Well, who's to say? Maybe they're being chased by a bear. So for part A, my run appears, mine's blue. If you're not sure, again, for the colorblind or your phone is broken and only not showing color. This is my run right here, and I can literally draw a line through it. My friend's run is the other one. So my run appears to be linear. Therefore, I am running at a constant rate. My friend's run starts slower than me, then increases and runs faster than me, then slows up a little at the end. Probably slower than I'm running, as it so appears. But they're still ahead of me when it comes to distance and time. After an hour, I've run 5 miles, they've run 6 miles. And I don't know if we're supposed to describe all that, saying how far we've actually gone. But they're a mile ahead of me. They're slowing up, though. Now they're doing this. Why might a person not run at a constant rate? Bunch of reasons. Terrain. A person might not run at a constant rate because of change in terrain, and that also means like elevation, going up and down, going to rocky to smooth, and going like that. Tiring out, or I'll just say stamina. Changes in stamina. Exercise routine. I don't know. Whether you want to compete in a certain sort of way. So motivators, etc. There are a lot of different reasons why you might change your running speed. You might just do it by accident. And accidental changes. I'm pretty good. Like when I do running, I'm pretty good at accidentally running the same speed the whole time. You know what I mean? Maybe break, plus or minus 0.1 miles an hour. But for the most part, I'm pretty good at it. Oh, part B. Hold on a second. Find the domain of each function. Oh, so that is a part of this. Find the domain. Describe the domains using the context of the problem. Now, the domain is, for each function, domain's the same, assuming we end our run there. So this was part A. So part B, I don't see, range is more interesting to me for this problem. Range says that I've only ran 5 miles, they've ran 6, whatever. But the domain here for both of us, and time is X, we start at time 0 and we finish at time 60 in terms of minutes. This states that we both ran for an hour. We both ran for an hour. 60 minutes. The range is much more interesting to me in that way. Where we finished, right? What distance we covered. So they didn't ask for it, so I'm not going to say it. All right, number 53. 53 and 54. I think these are the last two questions. Describe a real-life situation for the constraints. The function has at least one negative number in the domain, and the domain is continuous. So wait a minute. Oh, has at least one negative number. I'm like, to have exactly one negative number and continuous probably isn't going to be easy to describe. I was like, impossible. Next question. But at least one negative number. So when you're talking about, like a graph, something like this, the domain has a negative, maybe a -1 right there. So it does this and it's continuous doing something, but we start in negative land, right, on that one. So what we're trying to think about is the domain is continuous. Describe a real life situation. This is like, if we were talking time, when would we have negative time to talk about something? If we could purchase a negative amount of something, selling an object versus buying it or something like that, right? I want to think in terms of time here. I like to think of, although time 0, time 0 doesn't need to mean, time 0 can just be the present, right? Right now, I have this many calories, whatever. A minute ago or an hour ago, I had this many calories on me. You know what I mean? So an hour ago is that. So negative domain, negative elements in the domain. Let's see. This could represent time, where negative time, such as -1, represents an hour before a current event is happening. I wasn't being specific about a situation, so let's do one. Example, an hour ago, let's see, it needs to be continuous. I weighed 200 pounds, and now I weigh an hour ago. How about a week ago? A week ago, I weighed 200 pounds, and now I weigh 190 pounds. You lost 10 pounds in the week. This graph clearly doesn't represent that, so let's flip this thing over. The negative flipped over. There's my weight fluctuation right there. I don't like that we're ending on open-ended questions such as these. Number 54, I want challenge, but not thought-provoking. I'm really bad at this. The function gives at least one negative number as an output. The domain is discrete. So in this case here, we're talking about an output somewhere in the negatives, right? We might do something like this, but they don't actually connect, and they do that. So we can't probably use time for this scenario, and we have to say what comes out as a result of something. We probably can't use like a negative weight, right? We can do positioning, but positioning based off of something here that needs to be discrete. It can't be a time thing. It's very, very hard to indicate in terms of time. You can think of sales of something and how you lost money as a result of it. I have so much trouble with this, and I don't want to pause for the very last question. I want to think. Okay, I'll think of sales, but why do you lose money over time when it comes to sales? Well, because of productivity or whatever. Your poor management leads to a decrease in profit after each sale. Your poor management. Okay. You know when consoles are sold, like PlayStations and stuff like that, what they tend to say, and this might be, I think it's true for fast food restaurants as well. I'm going to be quick with this. That they tend to lose money on selling consoles. Like when they sell, I don't know if that's true anymore. I think for the PlayStation 3, that was the case. I don't know for PlayStation 5, but let's say it was. That they lose money for every console they sell. Sony. So why would they sell consoles if they lose money doing it? Now remember, it's not that they make the sale, now they lost money. It's that it cost more to make than it did that they're than they did they're selling it on. So why would they sell them? Because they make money back in other ways. Games, accessories, subscription fee, stuff like that. So they make money in different ways. Fast food businesses, I believe burger places tend to lose money on their burgers, but they make money back on their fries and their soda, stuff like that. So as long as you do that kind of thing. But this one, I want to do this way. So not your poor management, but for every video game console that a company sells, they lose profit. And after selling let's say 5,000 consoles, they are now down, I don't know, $2 million. I don't have these things as they are, but let's say after 4,000 consoles, now they have that. I don't know why they'd be down so many based on that many consoles, but yeah, let's do it. All right, guys, that's where we're going to end this one, and that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. The open-ended ones really threw a wrinkle in for me, and that's something that you can really work on. I don't have the creative bones that you might. I just want you to make sense of the information. What makes that one discrete, that last one, is you can only either sell the console or not, and it kind of makes sense in the situation. We can't have negative height. Sorry, you can. You can have negative weight in some ways. You can have negative height if you're underwater, underground, something like that. So you got to think about those. Thank you so much for watching. Take care. I'm going to see you in the next one.